Hey students, welcome back. This is 5.2. We're going to talk about rate law. In the last section, we talked about calculating rate. Now we're going to learn what we can do with how we calculate rate. So we're actually going to be figuring out rate law. And if we kind of just jump back in or jump right in, rate law tells us it tells us how a reactant will affect a reaction. So if I add more of this, what will happen to the rate of the reaction? That's what our rate law is about. And it actually covers all of the parts of a reaction. It could be talking about, like, mainly most of the time we're talking about our reactants, but sometimes we talk about a product because sometimes that changes our reaction rate, but we won't get into that right now. So our generic rate law is right here. Rate equals K, and then the concentration of A raised to the N, and we're going to talk about each of those parts. So we already figured out how to calculate rate. That was our change in concentration over change in time, but sometimes that's not enough for us, right? And so we're going to talk about our rate constant. Now, this is specific to each reaction and at that specific temperature. So it's got to be at a certain temperature for it to be constant. But those are the constants. So it's for the reaction and at its temperature. All right. Oh, look at that. And our units reflect the overall reaction order. Our units are going to reflect our overall action order. And that kind of tells the person of the rate law what order we have of the reaction. But now we've said some things about reaction order and we don't really know what that means, but our reaction order shows, whoa, I was in highlighter, my bad. All right. Our N shows how that reactant affects the reaction. Okay. And so if I double that, will the reaction rate double, or will it triple or quadruple, or what do we got going? Or will it have no effect? Because sometimes that happens too. So our three common reaction orders are 0, 1st, and 2nd. That's not to say those are the only three. Please hear me out there. There are more than three, right? We could actually have a negative to the first order, and we can have half orders, but you don't see those very often in AP chemistry, but sometimes they do come up. So I'm just saying these are our most common ones. So a 0 order reaction, so if we look at our rate law, because if we look at this mathematically, it should kind of help us out. So if this number up here is 0, anything to a 0 power is 1. So if I have a reaction order of 1, how will it affect the rate? There will be no effect, right? No effect. Hopefully that makes sense because 1 would be there. All right, let's do that same thing looking at this one. Rate equals K times A raised to the 1st. So if I double A, what's going to happen to my rate? It's also going to double. All right. Okay, now what about a 2nd order? So if we look at our example here. Ooh, so if I double A, so if I go from 1 to 2, 2 to 4 now, so this would be quadruple, right? Ooh, so it's going to affect it greatly. So those are the ones, if we're trying to have our reaction order sped up, we want to use those most possibly. Now, the last thing there is the sum of the powers of the reactant concentration. So the sum of the powers of our reactant orders, this should probably say orders, that would make more sense there, is the overall reaction order. Okay, our overall reaction order. So now, real quickly, how do we figure out these reaction orders? There's a couple of ways we can do that. We can do that graphically, which we'll find in our next one, or we can do it based on information that is given to us that has been determined experimentally. This can only be done experimentally. We can't look at our balanced chemical equation and be like, oh, it's first order, all right? It's not how it works. So let's check this out. What we do Let's take a look at our reaction, then we'll talk about what we do. So we have the reaction between NO2 and CO, giving us NO and CO2. Then we have so what they did was they performed the reaction 4 different times, it looks like, right? We have 4 trials. I'm going to number these. Okay. And then they took the initial rate. They measured the initial rate, whether it was spectrometry or polarizability, but they figured out the rate at that point. So what you can do is kind of compare what happens when you changed one of the variables. All right. And that's really what it goes down to. Once you get really good at this, you should be able to just kind of look at it and see. But for the first few, we're going to kind of go over them together and do all the work there. So we're trying to find the rate law. So if we look at experiment 1 and experiment 2 for right now, we see that we doubled NO2, but our CO stayed the same. So if we see what happened to the rate here, we can figure that out. A very mathematical way, because a lot of times the AP exam asks us to show how we found our rate. So one way we can do this is if we set the two equal to each other. So we have our generic rate law. Rate equals K times the concentration of NO2 raised to some power. I'm going to call that M right now because we don't know it. And CO raised to the power of N. Again, those numbers we don't know right now. But if we compare experiment 2 over experiment 1 by placing those numbers in there, we can do that. So let's see. If we go 2 over 1, we're going to say 0.0082 over 0.0021 is equal to K over K. Guess what? Those K's are constant. They are going to cancel out. Then we have the concentration of NO2 to the M and concentration of NO2 to the M. And then I should be putting those concentrations in there. So we'll go back to those. Boop. All right. So we're talking about NO2. So we've got 0.20 over 0.10. And then we've got the same thing with our CO, right? Except this one's 0.1 over 0.1 raised to the power of N, right? And we can put those outside the brackets. That might make more sense to us, right? If we put it outside the bracket. So if this is 1 raised to any power, right? It's not going to affect it, right? So that goes away collectively. So basically we're left with 0.0082 over 0.0021 is equal to 2 to the M. So this is 4, right? 2 to what gives me 4? Well, M in this case is 2. So we know it is second order with respect to NO2. Let's do the same thing with our CO. Where's one where CO stays the same, but our NO2 stays the same, but our CO changes. If we compare 3 over 2, right, that would work for us. Change the colors here. So now we have rate equals still K, but we could also use our knowledge that we already know, right? But it's sometimes easier. Miss Griffith is not writing very well. There we go. See you. Okay, so we're going to do that same thing. We're going to compare 3 over 2. So if we go 3 over 2, we've got 0.0083, one I didn't highlight there, over 0.0082. That looks like 1, right? We'll come back to that. And then we have K, right, over K, so those cancel out. Then we have 0.20 over 0.20. And even if it's raised to the second power, which it is in this case, sorry, I did not mean to open that, it's still 1 to the second power, right, which gives us 2, right, which really doesn't make a difference to us. Okay, and then we have 0.20 over 0.10, right, raised to the n. So this is going to cancel out as well. And so we have 2 to the n raised to the 1. Well, so n in this case is 0. So our rate law is going to be rate equals K times NO raised to the second power, and then we have CO raised to the 0 power, or we could just eliminate that altogether, right? Because 0 power wouldn't show up in the overall reaction. All right? Awesome. Now that we know that, we can now solve for K. All we have to do is choose a reaction, or excuse me, a trial, and just plug in and solve for K. So raising this up just a little bit, we have rate equals K times our NO2. This was our rate law that we just wrote up above. And let's say I haven't used experiment 4 yet. Let's go ahead and use experiment 4 because why not, right? And then K, and then we have NO2, which is going to be 0.4 squared. That is not where I wanted that squared. Okay, 0.40 squared. All right. So that gives us, on this side, we've got 0.033 K times 0.16. And now if we're isolating, we're going to divide by 0.16 on each side, right, to get us to K. K is going to be equal to 0.033 divided by 0.16, which gives us 0.206. I saved one too many sig figs, so let's say 0.21. Now we have to figure out our label on K, all right, because we need our appropriate label. Now what to do there is we can just go back and plug in, like kind of as an aside, we know rate's label is molarity per second, right? We know K is what we're looking for, so we're going to leave that there. And then we know each of these, well, we have that squared, right? So on this side we have molarity squared, so we're going to divide by molarity squared on each side. One of these is going to cancel out, and so K, for a second order reaction, is going to have the label of molarity -1, seconds -1. So then we just go ahead and put that label on there, and there's our answer. Awesome. Let's try another problem. Okay. So in this case, we have our initial reaction right there, measured at several different concentrations with our tabulated results below. We have our different trials, so I'm going to number these again so we can kind of be on the same page when we talk about them. All right, and let's see what we got. We're supposed to figure out the rate law and then the rate constant, K, for the reaction. So if we look, I'm looking there, if I am trying to find CHCl3, then I can just compare experiments 2, right? If I do experiment 2 over experiment 1, that should get me where I need to go for CHCl3. So we've got experiment 2 over experiment 1. Remember our generic rate law? Rate equals K times our concentration of CHCl3 times our concentration of Cl2. All right, so we've got 0.0069 over 0.0035 equals K over K. Remember, those are going to cancel for us. Then we have 0.020 over 0.010, and that's going to be raised to our m power. And then we have 0.010 over 0.010 raised to the n, and that's going to cancel out for us. So we have 2 to the m is equal to right around 2, right? So m is going to equal 1. So right up here, instead of m, woo! Did I blow that up too fast? Probably so. That's going to be 1. All right. We're going to do the same thing with our Cl2. What 2 should we compare here to find this one? What if we go... Well, we need where CHCl3 stays the same. So if we go 3 over 2. All right. So let's see what we got there. So we've got 0.0098 over 0.0069. See, this is not going to be the nicest little answer there, but we'll be all right. We've got K over K, right? And then we have 0.020 over 0.020. raised to the 1 power. We might as well plug that in there since we know it, right? And then we have 0.020 over 0.010. And this is raised to the n power. So these are going to cancel out. So if we take 0.0098, it's like 1.4, right? There. And then we have 2 to the n is raised to that. How are we going to figure that out? Or maybe you guys have already figured that out. And what do we get there? 2 to the what? If we take that, we should get n equal to our 0.5. So remember, I said that not always would we get what we thought we were going to get, like 0, 1, and 2. Our numbers are not always super nice, but we do get n to the 0.5 here. So again, blowing this up here. And this is going to be 0.5. Oh boy. All right. So now we can write our rate law. Here's our rate law. Rate equals K times our concentration of CHCl3 raised to our 1. So we could either put 1 or we could leave it off, your choice. And then we have Cl2 raised to our 0.5 power. Or we could even take the square root of it. That would work as well, right? Because 1/2 is the square root. All right. Then we're supposed to find our rate constant. So again, we can pick any of them. I like 1 this time. So we've got 0.0035 is equal to K. This one we're not asked to find our label of either because it gets a little weird, right? So we don't have that situation on this one. So we got 0.010 times 0.010 raised to the 0.5. All right. So we're going to go, and that's going to give us 0.1 here times 0.01 times K. Then we're going to divide by 0.001 on each side. And we should get a K of 35. Sorry, my number's written a little rough there. 35. All right. Awesome. All right. See you next time.